SwayamPrabha. Digital India. Educated India.
So, hello and welcome back to another lecture on Introduction to Soft Matter. And in the last class, we were discussing the simple shear flows, and we are going to continue the discussion. And there's a particular reason why we are continuing this discussion. That's because we want to understand a couple of very important terms that are related to non-Newtonian flows and polymeric fluid flows. Okay. So last time we were discussing this idea of the simple shear flows, if you recall, and here we had said that the function u is a function of y and is given by the flow field is given by these velocity fields, right, where we have written it down in the component form. So you have u, v and w as the velocity components. So now let us say that we have a isotropic simple fluid in a simple shear flow. We know the form of the velocity field, right, but the question is what is going to be the form of the stress tensor, right. So we want to now understand how the stresses in the fluid are going to develop. Now the general form, so let us say the general form of the stress tensor then is, so let us say we have a stress tensor. I am just going to write it in matrix form. So I just put this bracket, which means that I am going to write it in matrix form. So obviously the flow is 3-dimensional, right. So your stress tensor is going to have 3 into 3 components. The question is what are these different components? So in a simple shear flow, as we saw, that the flow velocity is basically the third dimension is not that important. So you are not having any flow in that direction. So the flow is essentially, in a sense, it's a 2-dimensional flow, right. Now here what you will have is, in a general case, you will have, so in the Newtonian case, you will have a shear stress. These are going to be symmetric because we have already discussed that, right. That the stress tensor for a fluid element is going to be symmetric due to the application of the principle of linear angular momentum. So these are going to be there, and the question is what is going to be in these two positions. Okay. Now if this was just a Newtonian fluid, you will only have the pressure terms contributing to the normal stresses here, and they would be equal in that case. But here in the more general case, you can have pressure, you can have force stresses that are going to develop in these directions, right. And since this is basically a 2-dimensional flow, your other terms are basically 0. You cannot put a 0 here, by the way, because even though the fluid is flow is 2-dimensional, you still have a pressure term that will contribute to a normal stress. Right. So this is the most generic form of the stress tensor for a simple shear case. Now the quantities that are of interest here that are of experimental interest R, and here say, so one of the quantities is obviously the shear stress, right. We have already written that down, tau xy. And then you have two other important terms which are called the first normal stress difference. Sorry, I wrote a double L in normal, this is only one L. And similarly, you have another term which is going to be called the second normal stress difference. I'll define mathematically these terms in a second here. Okay, so the first normal stress difference is the difference of these two components right here. So tau xx minus tau yy. Right? So let us write that down. So this is tau xx minus tau yy. And similarly, the second normal stress difference by a similar logic would be tau yy minus tau zz. Okay. Now they are important because they are the three independently accessible values in a simple shear flow. Okay. So important because they are the three independently accessible values in a simple shear flow, experimentally accessible. Now, going back to this, as I had said before, that if it is a Newtonian fluid, then tau xx minus these normal terms, tau xx, tau yy and tau zz are only the pressure terms, right. So they are actually the same. And for a Newtonian fluid, your first normal stress difference and the second normal stress difference is 0. But that cannot be said so for a more generic case. So in a more general case, you can have a finite first normal stress difference and a finite second normal stress difference. And this, you have this shear stress obviously in all cases. Now the shear stress here, so this shear stress must be an odd function, right. I mean, you can look at that, you can probably figure that out from a physical argument, that if the direction of flow changes, then tau xy sign should change its value. If the flow remains exactly the same, but the direction of u is reversed, then tau xy will have the same value, but with a different sign, right. So this will be an odd function. So maybe we can write this tau xy as some gamma dot. This gamma dot is the generalized, is the shear rate, and you have some eta which is a function of gamma dot, right, where this eta is how we define. So when we write gamma dot in the bracket, it means that eta is a function of gamma dot, right. So eta is basically a function which is given by this, and this can be called viscosity. And now this is an even function, right, because tau xy is a odd function and you have gamma dot. So if both the signs reverse, then but the sign of eta will remain the same. So this is an even function. We can also argue and show that tau xy so the first normal stress difference, tau xx minus tau yy, and I am just going to complete this in a second, and the other one, which is the second normal stress difference, they are actually even functions, right? And you can write this as sum n1, which is an unknown function, which is, and it is dependent on gamma dot. So, this is the first normal stress difference is equal to n1 and the second normal stress is equal to n2, and these are even functions, but they are 0 at gamma dot equal to 0. Because of this particular functional form, you can write this as, so once you have made that a particular observation that n1 and n2 must be even functions, you can write them as further n1 of gamma dot, and I will write both of these together because they are actually the exact same expression is there. So, it is an even function. So, I can make that even function by selecting, so most likely it suggests that it is gamma dot square and multiplied by some mu 1. Okay. I am not going into the derivation of why it is exactly like this, but I am just trying to physically argue that these will be even functions, and so this is a functional form that satisfies that criteria. Okay. So, now see, whatever be the values of where mu 1 and mu 2 are two new functions that we have introduced. Okay. So, n1 and n2, which were the normal stress differences, are now being expressed in terms of some mu 1 and mu 2, right? And these two, mu 1 and mu 2. So, from here we can, so mu 1 not, okay, this is mu. Okay. So, we have two functions here. Okay. So, mu and mu 2 are called the first and second normal stress coefficients, okay, respectively, obviously normal stress coefficients. And they are important because they are material properties. Now, the reason we are discussing these normal stress differences is because this is one way in which complex fluids or viscoelastic fluids start to differ from the Newtonian fluids, right. And this leads to very interesting effects, and hence they have to be accounted for. And the normal stress differences, now that you are seeing that they are important material properties, means that you can use these experimental observations to actually, in a sense, quantify the fluid. Right. So, n1 and n2 are, as we had discussed earlier, they are independently accessible, so they are experimentally accessible, right. So, these are quantities that you can measure experimentally. Once you have done that, we have said that these are going to be some values n1 and n2, and then we further said that these are even functions, and this functional form we did not derive, but this is let us just assume that this is correct at the moment. You can look at it, look it up later in a more advanced course why this particular functional form, but it is going to be gamma dot square multiplied by mu 1 and mu 2. So, the purpose here was to introduce these two important material functions. And secondary, these normal stress differences do lead to very interesting effects in these fluids, and we want to in today's class we are going to discuss a little bit of that. Just on the same ideas that we were discussing, the non-Newtonian fluids do show some very interesting experimental phenomena, which are experimentally observable phenomena, which puts them very apart from Newtonian fluids. And there are many such, and one of them very famous effects is also called the rod climbing effect or the Wijnberg effect. So, I am just going to list out some of the classical effects where the behavior of the Newtonian fluid starts to be in strong contrast to that of non-Newtonian fluids. Okay. So, classical phenomena. Classical phenomena related to complex fluids. Okay. And one of the primary ones that we are going to discuss today is also called the rod climbing effect. In this effect, what happens is, let us say you start out, there is a beaker, and in the beaker you have put a rod. This is, let us say, a metal rod, and you have a fluid. Just a second, let me draw this a little bit better. Okay. So, this is, the beaker is filled with fluid, and what you are going to do is you are going to make this rod rotate at a certain angular frequency. Now, if this was a Newtonian fluid, what would happen is the centrifugal forces will force the fluid to flow outward or away from the rod, and the meniscus dips a little bit. Okay. So, these are all radially outward, and the meniscus dips. So, this is what behavior you will see if you have a beaker full of Newtonian fluid. But let us say you instead have a beaker full of a polymeric fluid. So, this is a Newtonian fluid, and this is some polymeric fluid is there. And I am using the example of polymeric fluid deliberately. It need not only be a polymeric fluid, but I will show you an experimental result from our lab which relates to polymeric fluids. That is why this effect is nicely visible in that. If you have a polymeric fluid, then under certain conditions what can happen is the flow can start, the polymeric fluid can start moving towards the center, and as a result the meniscus actually starts to rise up this rod, and that is why it is called the rod climbing effect. It can be seen for polymeric fluids and for other type of fluids also, but in our lab, so what Naveen and Udita from our lab, they did a very beautiful experiment where they captured this on camera, and I am going to show you some of the results. That is very nice, but this effect is not only restricted to polymeric fluids, but it is possible in other ones. But the reason I am talking about this right after the normal stress difference is because this phenomena is usually linked to the normal stress difference that is present in these kind of fluids. This effect was first described by I think Garner and Nissan and by another person, Russell, but although it was known in the paint industry for quite some time. And then later on there was a very famous paper by Wijnberg on this particular topic where he explains this phenomena, and this effect, rod climbing effect, is also known as the Wijnberg effect because of that. There is another related effect which is called the Quell effect. And in this system, what you can have is, let us say you have a beaker, maybe I will use another color just a second. And instead of a rod that is partially immersed, you have, let us say, an impeller here inside, that is fully submerged and you have fluid in this. Then when you start rotating it, what can happen is you can start to have a bulge here, and because of secondary flows that can occur in this region. Okay. And this effect is known as the Quell effect. This is, we do see secondary flows even in our Wiesenberg the rod climbing effects system. So, we will show you that as well. Now, there are many other classical effects that you might come up, you will probably encounter when you start reading up about non-Newtonian fluids, and for example, there are other ones which are there, which is, for example, there is a effect called the dye swell effect. In the dye swell effect, what you have is, let us say you have fluid coming out of a very thin pipe. If it is a Newtonian fluid, the extrude, the fluid that comes out has a diameter that is almost the same as the inner diameter or the diameter of this particular tube from which it is coming out. But in the case of strongly non-Newtonian fluids, what can happen is that there can be a very big bulge in the fluid system as it comes out, and that is why it is also called the dye swell effect. There are similar other effects called the elastic recoil and the Ubler effect, but we can't go into all of them. What I would like to do is I want to show you a couple of interesting results from our lab, and I would like to discuss some of the important papers related to that. So, going back to the rod climbing effect, we, as I said, two people from our lab, they did an experiment, Nitin and Naveen and Udita, and what you have here is this a rod, okay, that is partially immersed. This is a rectangular beaker, and you have a polymeric fluid here. Okay. So, you have a polymeric fluid that is there in the system, and this is a rod, and we are going to rotate this rod at a particular angular velocity. Now, this is PEO, polyethylene oxide, 1% of polyethylene oxide. So, we took a powder of polyethylene oxide and we dissolved it in water to create this volume of fluid, okay. And it looks red because there is a dye in here for better visualization. Okay. So, that is why it looks red. So, let me play this video and then I will explain. The rod is stationary now and it is going to rotate. So, I hope you saw how this meniscus rose here, right. So, this is called the rod climbing effect. If you go to higher frequency, if you go to higher polymer concentrations and higher RPMs, this effect can become even more drastic. Here I believe the omega is something, so it's the rod is being rotated at around 1000 RPM, and once the rod stops moving, the fluid just goes back to its original rest state. Okay. So, let us just quickly look back at it one more time, what we saw. So, just a second. Okay. So, this is the fluid at rest. You have the stationary meniscus which is formed right around the rod, and we will see the difference. So, that you can see clearly this very large rise. So, this is the rod climbing effect. Now, in our lab we did another experiment. So, this is a slightly different experiment where the camera was positioned at a different angle, and here this is the original. So, this is polyethylene oxide. Once again, it is colorless in this case because the dye has not been mixed with it, and we have the rod which is partially dipping, and you can see there is a gap between the rod and the the floor right here. So, we are going to start this video. So, this is, by the way, this is the die up here, and what I would like you to see is how the die where the die gets advected. Okay, so, the rod has started rotating, and you can see that the die is slowly coming down. There is a very strong flow, and the flow the flow goes here, and so you can see this die is forming a very beautiful conical shape over here, and here the die is spreading out slowly because of the fluid flow. The rod is still rotating, by the way. So, the die is slowly spreading due to the fluid movement, and you do have rod climbing effect right here, but because the camera is from a is looking at this whole setup from a different angle, you cannot see that. Okay. So, that part is not visible over here. So, you can, at the moment you can see only the fluid flow, but both of them are happening simultaneously in this experimental system. And again, this video is thanks to Naveen and Udita. And you can see this video is real time, and the die seems to the periphery of the die seems to not be moving anymore. It is actually moving, and it is moving very slowly. So, it shows that there is a strong recirculation region here, right. So, you can it will be up to fluid up to diffusion partly to take this die to the other locations. You can see the circular movement at the top. There are some bubbles which are just moving round and round. Okay. Okay. So, this effect so one of the very important papers on this particular topic was written by Weisenberg, and that paper is titled A Continuum Theory of Rheological Phenomena. It was published in Nature in 1947, and Weisenberg says that when materials of different kinds are subjected to mechanical actions, we may observe a great variety of rheological phenomena, and we shall confine our attention here to a certain group of them, which allows a theoretical and experimental investigation on a macroscopic scale. Here then, as in the classical theories of elasticity and hydrodynamics, we can treat the materials as continuous media and the forces and displacements as vectors which vary continuously in space and time. So, he is considering this entire, he is going to consider this entire phenomena from a continuum perspective, and that is what he lays down in the introduction. And then he goes on to say that let us consider first what happens in an appropriate chosen cycle of rheological states. We start with a material in a ground state, that is in a state in which every portion is at rest and free from external forces. So, we started our experiment also from the ground state, where everything, there was no externally imposed force on the system. And then we saw that the rod climbing effect happens once the system is not is removed from the ground state. So, when we impose some mechanical action. So, he also goes on to say we then impose some mechanical action and thereby bring the material into a particular energized state, the phenomena of which we want to investigate, right. So, finally, to complete the cycle, we suddenly release all external forces and allow the material to drift back into some ground state. You can see that this is very similar to the ideas that we had developed at the beginning of the class with the stress relaxation and the stress control tests, where we apply some stress and then we release the stress and then we see what happens, right. So, it is a very similar idea to what he is discussing over here. And he goes on to discuss about recoverable strains, etc. There is a couple of important things I would like to note, and it is this particular figure. Okay. So, here he says flow of liquids under the actions of stationary shear in gaps. And he goes on to list many different types of experimental conditions. The one that is particularly valid for us is this particular number 3, where we have this beaker and then we have this rod that is immersed, partially immersed into the fluid, and we would have this rod climbing effect. And he shows that under very high, for example, this is the ground state and this is the low speed state, and at very high speed states you can also have a very strong rod climbing effect that you can see. Okay. So he goes on to list many other cases over here. So this manuscript, if you wish, you can take a look at. There are a couple of important lines that I would like to draw your attention to. So over here, for example, he will attribute this partially to the normal stress. So he says that an analysis of the experimental results shows that in such a motion the stress has its strength so distributed over the various directions in space as to comprise, in addition to the shear stress components, a pull along the lines of the flow. Okay. And then furthermore, he goes on to say here that if, as in our experiments, the lines of flow are closed circles, the pull along these lines strangulates the liquid and forces it inwards against the centrifugal forces and upward against the forces of gravity. So he is trying to explain the phenomena. Our purpose here is not to go into a whole lot of detail like the exact mechanics of this, because that would require understanding the exact nature of forces and deriving the conditions of that. But I wish to give you a good introduction and show you where some of the important manuscripts of this are of this area are, so you can look at it yourself. The other important thing, as I had said just before, that before him there was another couple of gentlemen who had performed very good experiments, and they had talked about this particular phenomena, and that is Garner and Nissan. And you can see that in this article he actually thanks Garner and Nissan, and he says Dr. Garner and Nissan, who on being informed of the results obtained and while continuing their own lines of research, suggested a useful arrangement of pressure gauges. Anyway, so let us quickly look at Garner and Nissan's paper as well. So Garner and Nissan's paper was titled Rheological Properties of High Viscosity Solutions of Long Molecules. Right? So these are the macromolecules that we had talked about, and this appeared, this had appeared in Nature, but a year ago. You see, 1946 is the year of publication. And if you want, you can go through this manuscript yourself. I just would like to draw your attention to one of the final paragraphs here, where they talk about this secondary flow. And they say that this is observation number 5, that finally the secondary flow can be observed visually as it takes place on a macroscopic scale in certain circumstances. A flat disc may be fixed parallel to the flat bottom of the glass beaker at say half centimeter distance from it. The beaker is then filled with a solution of rubber in benzene or soap in hydrocarbon of fairly high viscosity. On rotation, it can be observed that there is a secondary radial flow from the periphery of the stationary disc inwards, both above and below the disc. Small colored particles will reveal the flow readily. Similarly, on rotating a rod partially immersed in such solutions, the liquid will be observed to climb up the rod from the line of the strain to the regions of no strain. So here he is also discussing the rod climbing effect. So anyway, these are some of the original manuscripts of this area, and you are welcome to download these and take a look at this in more detail at your leisure. In the next class, what we are going to do is we are going to head on into the lab. So today we had a mix of looking at some of the experimental results and theoretical constructs that are relevant, and in the next class we will go into the lab and start doing some nice experiments for ourselves. Okay. So the next class is going to have a lab component. Okay. So we will end our class today here. Thank you very much.